Okay, today is a review of logs, and we're going to get into graphing of these logs, and then the test that's coming on Wednesday, that's about graphing. Now, you may have forgotten that we did some exponentials before. Remember how you'd have these guys? They're an exponential. It was y equals like 5 to the x or whatever. And those, we never tested you on graphing because there really wasn't much to test you on. So now we're adding logs to it and testing you on that. So a log graph has a different parent function that you'll need to learn. And then you'll be tested on both the log graphing and the exponential graphing at the same time. And obviously logs and exponentials go together. In this example with the black one, the log problem in black is rewritten as an exponential in red. Now that doesn't have an x in the exponent, it bothered me a little bit, so I redid it like this, so that when we rewrote that, it was a to the c equals b. This is an exponential problem, and that is a log problem. Now to graph them is a whole different topic I want to get into, but I want to make sure first you get how to just evaluate them. Log base 3 of 9 is a super easy one. I know the answer. Boom. You know the answer. If you don't, then you just stuff lost it since I was here 2 days ago. Do you get that that 9 can be really written as a 3 squared? That's just simple substitution. In math, you're always allowed to do that. If you can substitute things that are equal, you can do that. So then, why did I do that? Because if this and this are the same, that's the answer. The answer to that is 2. Raise your hand if you knew that the answer to that was 2. Okay, good. Then, let's get a little more complicated. Log base 3 of the 4th root of 3 underneath a 1. Holy smoke. All you have to do is rewrite that as a 3 to some power. And usually they're fraction powers. And then the problem will say log base 3 of 3 to the something. Once you've got that fraction power, you'll have the answer. Yes. Turn it my way and I'll tell you if you've done it right. That's the one. You're close. Yours doesn't have the fraction aspect of it. It needs to be a fraction because we have the 4th root involved in it. And the roots go on the bottom of the fraction. Yes, that's the one I'm looking for. That's the one. Yep. 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 All right, so I'm going to help. This was really 3 to the power of. Why is it a fraction? Because this is a root. That's the 4th root of 3. So it's the 4th root. You put a 4 down there. The roots go on the bottom of the fraction. Does this 3 need to be put to any power to make it equal 3? Well, 3 to the 1st, I guess you could say. And the last thing is it's a 1 over, and that's a negative. So 3 to the negative 1. So, final answer, since these two are the same, that's the answer. All right, next one. Log base 5, 25, and I'm going to say equals x. Do a rewrite. Do the problem that way. You'll still be able to find what x is equal to in a different way. Do a rewrite. Just want you to see that these are really rewrite problems. You get that that's 5 to the x equals 25. And then can't you just kind of solve that in your head and go 5 to the second? X equals 2. See what I'm saying? All right, yes. If it didn't add up nicely and if it came out to like 26, for instance, is that what you're saying? Okay. So then, how would you do that in your head? You couldn't. Nope. So we wouldn't give you one that doesn't work out nice because you can't use a calculator. In the real world, what do people do? They use a calculator. And they would go, oh, log 26 divided by log 5. That's called the base change. Because right now it's a base 5. If you calculate again, base 5? No, it's base 2. So you take the log 26, which, if I say log 26, I didn't say a base, that means base 2. I'm getting beyond myself how to put it in the calculator, because you don't have to use a calculator. In fact, you can't use a calculator on this next step. All right, next one. Log. This is going to be the hardest one. Base 3 of, yes. Okay. log base 3 of 1 over the fourth root of 9. This one will be a fraction power, but you will need to reduce it to get your final answer. Once again, you just need to match the base, so I made it 3 to a power. That's it. That's it. That's it. Yep, yep, yep. Yep. Reduce that and you'll have it. Yep. I think. Is that a 2 on the bottom? Good. So, first thought is it's a fraction exponent and it's negative. Why is it negative? Because it's got a 1 over. Negative, and then what root was it? That's the root, fourth root. And then I got to take the 3 and somehow get it to a 9. That's squaring. But I can't leave it as 2/4 because that's not simplified, so therefore negative 1/2. All right. How many of you feeling comfortable with that part so far? Okay, good. And that's the main thing you're supposed to learn yesterday and the day before that. It was actually kind of on the easy side considering we gave you 2 days for it. Then you get to learn graphing logs. So this again is an exponential. This is y equals e to the x. Just to clarify, do you remember that e is about 2.7? Everybody got it to like 3 decimal places? 2.77 what? 18. 2.718. Okay? So if that is 2.718 dot 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 goes on forever, it's a number like pi. But you should memorize the first few digits of like pi. Nobody ever has e competition, so like pi. 3.14159236535897932386846. Anyway, nobody does that with e, even though it goes on forever too. It's kind of a the neglected, irrational number. All right. But anyway, if you were to graph this one, where exactly is this spot? It's got to be somewhere. It's got to be a specific number every time. Nope, that's not. Yes, ma'am? 1. Because you're putting in x equals 0. See, this is where x is 0 right there. And you follow it up and you get this number. If I put in a 0, anything to the 0 power is 1. So that's the kind of graph always touches that 1. This is just a reminder about this kind of graph. It had an absolute value. No, that wasn't called again. An asymptote. That's it. It has an asymptote across here at 0. Now, it's easy to forget which one's which. That's like the horizon. That's an horizontal asymptote. And then I gave you a dumb way to remember it. Remember? Anybody remember? Horizontal. So it's a what? A y equals. Good. So that's y equals 0. Okay? The one you're learning for today is logs. They're different, but they're related. Do you remember how if we reflected something across the line y equals x, that was its inverse? The inverse of this one is that. Reflected across that line, that dotted green line. Got this? That's its inverse. Now I should make it actually continue to rise. All right. That black one, that is the graph of log. Log base e to the x to be exact. The natural log. Okay, so now I just want to show you that those two are inverses of each other. You get how as they go across the line here, there's a spot, there's a spot across the line that matches up with it. They go directly across that spot. So this spot right here, if this was 0, 1, what's that spot got to be? 1, 0. And now think about it. Why? Because if you put a 1 in for the x, you're putting a 1 in right there, then here's a little saying. If you won the argument, you get nothing. This is a log. And if I put a 1 in the argument spot, just to clarify, that's the base That spot right there is called the argument. If you won the argument, you get nothing. I personally take credit for this one. It's probably going to work better when you understand it better. But if you put a 1 in right here, the answer will have to come up to 0. Let me show you why. If I don't have an x there anymore, I put in a 1. I can say equals x. Then you can rewrite it and say 2 to the x equals 1. And think about it. What power can I put things to that'll make it equal 1? 0. That's why I say if you put a 1 in the argument, that's that spot right there, then you will get 0. The answer will have to be 0 because 2 to the 0 power will equal 1. All right, so let me make you absorb that a little bit. Log base 73 with a 1 right there. What's the answer? 0, because there's a 1 in the argument. Why? Because if I say equals x, then I'm going to rewrite 73 to the x equals 1. What would work? 73 to the what? To the 0 power. So the answer to this must be that it would equal 0. Then if I add a 0 right here, 72 to the 0 is 1. That works. It must be 0. So the answer comes out to 0 if you have a 1 right there. If you won the argument, you get nothing. It also is true in life. Sometimes you have a friend and you're arguing about something like politics where you can never end up deciding who's right, and you can end up making an enemy out of your friend over something stupid like that. And you've won the argument, maybe in your own head. You make a great defense of your argument, but you just pissed off the other person and they don't believe you anyway. So you got nothing. That's true. A lot of the arguments that spouses get into, you end up arguing with them, arguing over something really stupid, and you have this point, and at the end, they don't even care. They're just mad at you. You just won the argument, and you got nothing. Okay, true math. Put a 1 right there. You get nothing. All right. So there's another couple little things you got to know about logs. You're not allowed to have anything right there that won't work in the log problem. So in other words, there's A, B, and C. This has certain rules, things it can't be, and this has certain things that it can't be. We just established that if you put a 1 in the B, you'd have a 1 in the argument, and you get an answer of 0. But B has certain rules, like you can't have a 0 there. And I'd like you to write the rules for yourself, because this is the easy kind of problem. If we were to throw one of these on your test, honestly, I have no idea if it's on the test or not. I just know if I were going to put a question on the test to try to test generally do they get what things are allowed and what aren't, I might make this negative, because you can't have negatives in the base spot, and you can't have negatives in the argument spot. There's no negatives allowed here or here. The answer could be negative, but the base and the argument, the other parts, that cannot be negative. All right? You can't have negatives in either spot. This spot can't be 0, and neither can this spot. And I wish we could just say, well, obviously if it can't be negative and can't be 0, that it must be positive. But it's not quite that simple, because it can be this one right here can be any positive. So there's no more rules. As long as you're not negative, you're not 0, you're okay. So in other words, B can be any positive number. But A, you can't just say that, because there's one more thing A cannot be. A is not allowed to be 1. The base cannot be 1. I'll show you why. Log base 1 of, let me think. Let's do that one, for example. Now, I know you're not able to do it in your head, because you're going to go, okay, I got to put 1 to a power and make it equal 7, and so I can't do that. But you might think you could do it on the calculator. Nope. Why? Because the calculator knows you're not allowed to have a base like that. You can't have a base be 1. One of the things you can't be. But here's why. 1 to the x has to equal 7. 1 to the x equals 7. You try taking a 1, putting it to a power, and make it come out to 7. If you take 1 and put it to a power, aren't you just going to times the 1 by itself a whole bunch of times? Can you make that turn into 7 then? No, that's why 1 is one of the things you're not allowed to have in the base. Okay? So both this spot and this spot can't be negative and they can't be 0. And there's one extra thing. This one, this base spot, cannot be 1. No 1s down there. Okay, so here's some quick ones that could be like just undefined. Log base 1 of 32. What's the answer? Undefined. How about, what if I change this to a log base? 3. Could you do it now? Yes. Could you do it in your head? No. Okay. How about now? Could you do it in your head? Yes, because 32 can be written as 2 to the 5th. 2 to the 4th is 16. 2 to the 5th. And therefore, it's the answer. Yeah, so that one's 5. Okay, what's the answer now? Undefined. Remember how I just said seconds ago? Can't have a negative there. And it's really easy to think in your head, somehow I'm going to make 2 into negative 32. Here's why. If I say equals x, 2 to the x equals negative 32. Think about that for a second. 2 to some power has to turn it negative? You can't. There's no number you could put there that would work. You could turn it into 32, but you can't turn it into negative 32 by putting it to a power. No such thing. So that's why we can't have negatives in the argument. But anyway, so as soon as you see that, you go, oh, undefined. All right, what other things could I put? Log base 7.93 of x is equal to 4. Did I break any rules here? No? It's legal? I think it's legal. Unless you can prove it to me. Are you just saying you can't do it in your head? Hey, watch. 7.93 to the power of 4 is equal to x. Even though it's nasty, I can do it. That's these calculations. I know you were thinking I needed a negative. I don't need a negative. 7 to some, it's just 7.93 to the 4th power. There's an answer. It's just really big and nasty and decimal. So it's doable. What about now? Not allowed. Can't have negative in base. Why can't you do that one? Okay, watch. Negative 7.93 has to be put to the 4th power, and it'll equal x. I know this one right here I could do on a calculator. And yet it's still not allowed. So that is something you also need to understand. Is some of these rules aren't there because they're impossible. It's because of whether or not the x is in the argument or the x is in the answer. Once you change the problem just to move this 4 over here and this x over here, now do you get it's an impossible problem? Because you go negative to the power of x has to equal 4, and I'm changing a negative number into a positive number, and that's not possible. And so the point is, they just made it simpler, said no negatives at all. Because sometimes negatives work, sometimes negatives won't. So they just made a rule, no negatives. That way nobody will ever get messed up. Okay, so these are not allowed to be negative. These are not allowed to be negative. And what was the one more thing? Can't be zeros, of course, either. What was the one last thing? 1. Can't be 1 where? Base. No 1s. All right. So now for the parent graph. This is the big moment you've all been waiting for. Sketch this one. It is a graphing test after all. So you have to know all those things I just told you, but even more than all that, you really need to know the parent graph. The parent graph, would you agree that this right here looks a little bit like a tree? Okay? Now, think about it for a moment. Do I ever call that a log? If you treat, okay, we're gonna stop here for a moment. I'm gonna pause for just a second. Okay, so back to the recording here, because we got interrupted there. Now, a tree, once it's like blown over in the wind, it's laying on the ground, then you could call it a log, couldn't you? So, here's what the log graph looks like. You see where I'm going with this? In case you get forgetful and you're like, I can't remember, is that a log or is that an exponential? Because they kind of look similar. That's a log. It's like a tree that's blown over in the wind. You won't by accident mistake that for an exponential. That doesn't look like a tree that's been blown over in the wind at all. The green one, exponential growth. You know it's supposed to go up a lot, right? You know, for growth, exponential growth. All right, so anyway, the green one's exponential. The red one, that's a log graph. And the parent has an asymptote just like the other one, except this one's a vertical asymptote, and it goes right at 0. That vertical asymptote is vertical, and therefore zertical, and therefore x, and therefore what is the asymptote at? X equals 0 is the asymptote. Now, do you think we'd ask you things like, what's the domain of it? Oh, yeah. What's the domain? From what to what? 0 to infinity. Good. What's the range of it? As in how low to how high? Negative infinity, positive infinity. Good. You guys are getting much better at those. You can just say them now. Okay. So domain and range are easy of this. How about if I was going to describe its end behavior? We have to use a limit. Let's talk about the right side. This over here, if I extend this out, the limit of the function as x approaches infinity. If it's on the right side, it's infinity. Then what's the answer? Equals, this is always the y value. This is the x. This is the y, or also known as the height. What is the height of my graph if I go infinitely far to the right? I know it may seem like it's leveled off here. It does not. It continues to rise very slowly. There is no asymptote to hold it back, and therefore I know it's rising. It seems like it's flat there, but it's slowly rising. It's just not rising very fast at all. Okay, so that means it's going to eventually go to infinity if you go far enough to the right. Okay. Now, left, right, up, down. Do you remember back to parabolas and you go like that and it would move the whole thing up 5? What if we wanted to move it to the left 5? We'd go in here and go like that. That would be left 5 and up 5. Remember what I'm talking about? Okay, these have the same deal. Y equals log, let's say log base 2 of x. And now if I decide to in by the x, notice I said in as in inside, by the x, go like that. This is a tricky one because a lot of people think, okay, I see a 3 at the end, and the thing on the end always moves it up or down. This is on the inside. It's inside by the x. Horizontal on the inside, high, low, remember this? And it's vertical on the outside. That would be if there were no parentheses here, and there was a +3, like, or +5, let's say, out there. That is the vertical on the outside part. Or if you put a number in front like this, that's also vertical. So now, this one I just drew. Green, that's the parent function. 1, 2, 3 changes that I make to it. I start on the inside, so I'm going to start in there. And what's that one mean? Left 3. And then I move to the outside, and I do them in order because that's what you should do. Yep, vertical stretch factor 5. Okay, now what? Up 5. So these logs are just one more parent function. It's just the same as all the others you've ever had. There's an inside part and an outside part. Stuff on the inside is in opposite order. So here's a way we could mess with it. Log base 2 of let's say 1 minus x. That'd be nasty. This has got 2 changes to it. You might think it's just like subtract 1. Is that the exact same thing as x minus 1? No, it's not. Put log base 2 of, what could I put that would make it easier to see that there's 2 things? Negative x plus 1. Very good. That's the same exact thing, but now it's easier to see that that's a reflection of flip. Remember, it's horizontal on the inside. Horizontal on the inside and vertical on the outside, but there's nothing happening on the outside. So this is a horizontal reflection, and then, or not necessarily and then, sorry. We actually would start with this one. And it's a left 1. Of the 2 things, the left one or the horizontal reflect, which comes first? The left one. Because normally we would do this first, but because we're on the inside, we can mix in opposite order. we'd have to do plus 1 first, which means you left 1. Okay, that covers everything that you'd have to know. Now let's actually do some of your homework together. I think you'll feel better once we've done the first few props. I'm going to pause and we do that. Okay, we found the worksheet, and number 1 is 5 to the x, and we're putting it on a XY chart because a sketch is not good enough. This is a graphing test. You need multiple points. In this case, we're only going to need 2 points. It's not that bad. So let's find one other point. Stick in 1. For God's sakes, that's easy. 5 to the 1 is 5. Right? And 1 right there. 5 to the 1 is 5. Over 1 up 5, there's a dot right there. And now, you have to know how to connect the dots with the right curve there. And I missed it pretty badly. I'm going to try that again. I'm going to try it with red. Alright, and I missed it again pretty badly, but I think the alignment on my board is off. But anyway, and one more thing you have to have, unless you want to lose 5% every time. What do you think of it? Asymptote. There we go. And that asymptote is at a y equals or an x equals? It's a horizontal, otherwise known as horizontal, tells you it's a y. Alright, so that's the asymptote, y equals 0. Okay, now let's answer some of these other questions. Domain. It looks to me like it goes forever in both directions. Would you agree? You put all reals. You could also say negative infinity, comma, positive infinity, parentheses. The range. Doesn't go forever downwards. What's the lowest it goes? 0, and does it actually touch 0? Parentheses on the 0 then. Up to infinity is correct. 0 to infinity is the range on this guy. The left end. Well, if you go to the left, it gets closer and closer and closer to what? So the answer is no, sorry. You're usually right, so you threw me off. All right. The left end does not get close to negative infinity. It's what? It's 0. All right. I had one person say 0, one person say negative infinity. I should have gone with the 0. The limb of the function as x approaches negative infinity, that's where the x is approaching on the left side, it will equal 0. On the other end, I will get you the framework. Limb of the function as x approaches, then equal. And you just got to fill in 2 things. This is how every limit looks. You just need a number there, and that's your x number, and that's your y number when you move way to the right. End. Okay. That's it for number 1. So each question is graph it and then answer a few questions about it. And there's 6 like that. All right. Let's move on to one that's actually a log. That was an exponential. Let's not do the next log. It's actually very easy. You can definitely do that on your own. Just remember that ln means log base what? E. It might not be as easy as I'm saying. Log base e of x. I know some people are going to freak out because that e makes them think, there's 2 variables. No, there isn't. What's e? 2.718. So really, you're graphing, and yes, it's fine with me if you do this. And I know math teachers across the world that are watching this video are probably twitching, going, that's not the same thing. No, I know, but it's as close as, it's close enough for making our graph. Do you think I'll be able to tell the difference on your graph between 2.718 and 2.7183529? I don't think so. You know what I'm saying? All right, so you can kind of generally use that as what e is. Okay, so then how am I supposed to graph this? I would personally make an XY chart again, and I would stick in some numbers. Like stick in, you want x to be, well, if you won the argument, this one, I'm going to put a 1 in for the argument. I'm going to get what? Nothing. I get 0 for the so 1 comma 0, but it'll be on the graph. Think about it. It's a log graph. It's supposed to generally look like that, right? It's like a tree being blown over in the wind. Okay, so the log goes through this, and I need one more point. Now, this one's the one that's hard for people, but all you have to do is make the bases the same, and then the answer will be the exponent, right? So what should I stick in for x? Since you could pick anything you want, 2.718. And when you put in 2.718 for x, it's the same as putting in e, right? 2.718. Then those two are the same. What's the answer? 1. So the point 2.718 comma 1 will be in the graph. Well, I know exactly if you did it perfectly. No, but I'll be looking for about 3 comma 1. Okay. And then, yay, I went through both points, and I better darken that one in a little bit more. As you can tell, I have 2 points, and oh, almost lost 5%. And I missed. I'm going to try again at the end there. And that's a horizontal. No, that's a vertical. So it's a vertical. So it's yes. So the right end behavior looks like as it goes to the right, it goes up towards infinity. The left end behavior, I know this one freaks people out. The left end, you're always thinking it's like going to be over there. But the left end on this one is the left side of the graph. So, and I could be wrong on this one, and I'm going to check for you tonight. I am not the arbiter of all math problems. This one might be getting here, but I'm feeling like the left end should be just right there, which is heading towards infinity, negative infinity, sorry. The left side of my graph is headed towards negative infinity. But I don't know if, since he doesn't ever go across that asymptote, if there is just an answer of no answer. But I will find that out. Yes? Yep, the volcano won. So it was like that. Right. So it's just that we always had a left end before. It's sort of like that, except what if it didn't have this side? Then what would the left end be? It would be this, wouldn't it? I hear you. So what you're saying to me is, and you very well could be right, and I'm going to check this tonight, but you're saying then that I should write limit of the function as x approaches 0 from the what? From the positives, that it would equal, when I get infinitely close to 0, it goes way down, right? It's heading lower and lower and lower. So it would be negative infinity. So really the question I got to look up is, I agree that that is a true statement about this graph. I just don't know if that would be considered the way to write it, the left end of it. So how about this? Does anybody check? If you're looking up the key, that'd be awesome. Look for problem number 2, see if that one happens to be the one that you get or not. Or if there's another one like it. Says this one. Way to go. You guys pulled it out. I would have been wrong on that one. My gut said to go negative infinity because it was the left end. But I get the left end of this graph. I'll have to explain that to my 3rd hour class. All right. So, any questions? All right. So, you now have, that is, you've learned everything you have to be able to pass the graphing. We just got to polish it up a little bit. I'll give you some more tricky ones, a little bit harder ones tomorrow. Sorry, we're not here tomorrow. Monday. Then Tuesday we have a review. Then Wednesday. Okay, that's planned for the next few days. That's all I got for the video for today.